Cool. So hi, everyone. Welcome to the next session of the P4 workshop. Today, we have a really interesting talk on P4 DPDK. The title of the session is, Can P4 run on Switchy CPUs? And here to answer that question is Cristian, Dumitrescu, and Wang, both software architects from Intel. Why don't you kick it off?
Okay, thanks very much, Brian. So hello, everyone. My name is Cristian. I'm a data plane software architect at Intel. And together today with my colleague, Han, we are looking on how to run data plane programs written in the P4 language on multi-core CPUs and still get the right level of performance. That's the key part. The question we are asking today is, can P4 run on Switchy CPUs? And just to cut the mystery short, I will give you the answer straight away. Yes, of course, we can run P4 programs on multi-core CPUs and still get a great performance. And we have already proven that with the P4 DPDK. So let's take a quick look and see what P4 DPDK is. P4 DPDK is simply a framework that is there for you to develop better and faster virtual switches or software switches, if you like, by combining the many attractive features and the flexibility of the P4 language with the performance that DPDK provides. So for people that don't really know what DPDK is, DPDK stands for Data Plane Development Kit. This is an open source project that provides performant drivers for network interface cards in user space, as well as some other data plane software libraries. So, Han?
So P4 DPDK is an open source project as well. It has 3 components. So at the moment, the source code for the P4 DPDK is stored in several different repos. The first component is the P4C compiler. That is, we contributed a new open source P4C backend, the P4C DPDK backend, to the P4C repo on p4lan.org. The second component is the DPDK backend, or in other words, the runtime that you can execute the P4 program, which is currently available in dpdk.org. And the third component is the DPDK target agent, which orchestrates the communication between control and data plane, which is also available on dpdk.org. Cristian?
Yeah, thanks, Hans. So basically, at this point, this framework is basically spread over 2 open source projects. They communicate, the P4 compiler works with this DPDK backend through an intermediate representation file that we'll talk about in a few slides. Let's go to the next slide. Before we look into a deeper way into P4 DPDK, see what the P4 DPDK is. Let's maybe spend a moment and see why exactly are we doing this. So because some people might say, yeah, of course, good, great, but why exactly do we need to run P4 on the CPU in the first place? So here is a good reason for this, which is building flexible infrastructure. So in a data center, you find lots of switches, right? Typically, big iron switches, they handle many terabits per second of network traffic. The CPU, on the other hand, usually sits in the sub-terabit per second range. Although there is a lot of commonality between them, right? So the virtual switches running on the CPUs are doing very similar things in similar ways as the big iron switches. The former are simply the smaller siblings of the latter big iron switches. Right? So wouldn't it be nice to have a framework that allows us to unify all these switches in whatever shape and size they come under the same P4 development environment. There are some obvious key benefits to this approach, which are simply better integration of all these switching layers, and also a better productivity for the team that maintains the data center. So it would also allow us, P4 DPDK, or this framework would allow us to finally liberate the virtual switches that switch traffic between virtual machines and containers. By allowing us to build custom virtual switches quickly and efficiently in P4, rather than either build them in RTL or for the FPGAs, or build them in millions of lines of code of C code, right, in user space or in kernel space. Han?
So to continue what Cristian has said, our goal is to provide a flexible infrastructure for P4 programmer. And the key to that is to enable P4 Runtime as the common control plane API for various of P4 target. So you may be familiar with programmable switch ASIC that's provided by Intel. P4 DPDK from a software stack perspective is very similar to the existing software stack that is designed for switch or even a SmartNIC. So at the bottom of this figure, you have 3 different P4 programmable target. These are a P4 programmable switch, a P4 programmable SmartNIC, and in this case, a new target called the P4 vSwitch, which is a P4 DPDK target. And on top of each of these targets, we're going to provide a device-specific driver and a device-specific control plane agent that can be used to facilitate the communication between the control and data plane. And across all 3 different targets, the P4 runtime is the API, and the user can write their control plane software across all 3 targets. And of course, the control plane application is going to run on top of the control plane. So the key here is you can write your control plane application once, and you can use them across different targets. So, this greatly improve the flexibility of the programmer so that they can decide where the functionality, the packet processing functionality should be placed. It could be on the switch or it could be on the CPU. It really depends. So that's maximizing their flexibility. Yeah. Cristian?
Cool, thank you. So here is maybe another reason that might be appealing to people where P4 DPDK could help, and that is building better network stacks. So this approach, the P4 DPDK framework, allows us to implement in an easy way a networking application as a switch that has a bunch of accelerators around it. So whether the application is a next-gen firewall, whether the application is a 5G UPF or BNG or AGF or some other application, it is typically the case that the application does a lot of typical data plane tasks like packet reception, packet transmission, classification, ACLs, feeds, tunnels, NAT, meters, traffic metering, right, statistics, etc. So these are all typical data plane blocks, and the development of data plane usually translates into a large part of the development effort. Therefore, it would be really nice to minimize, to reduce this effort of the development of the data plane part of the application. So the way to do this is simply to keep the data plane short and crisp in P4. Basically, put all the header processing, describe all the header processing tasks in P4 as a virtual switch, and everything else that doesn't fit well with the P4 constructs, things like cryptography or things like TCP proxy or TLS termination or TLS proxy, lawful intercept, video optimization, traffic management. deep packet inspection, application identification, heuristics, all sorts of stuff. These things can simply be around this the switch that is described in P4. The switch also connects, besides these blocks, it also connects with the NICs and other hardware accelerators. The advantage, of course, is that nothing is predefined. Only what you actually need to use is used, as opposed to have a big, bulky network stack with lots of protocols that you don't really use, that might have an overhead over there on performance. Here in P4, everything is dynamically defined, whether it's protocols, whether it's packet metadata, tables, actions, the flow on the data path, etc. Everything is dynamically defined. And we also typically decouple the data plane from the control plane. The two communicate through the standard P4 Runtime RPC interface, as Han also presented on the previous slide. So I think now I'm going to go in more details and talk about the current P4 DPDK feature set. And then on the next slide, Han will get into more details on how P4 DPDK really works under the hood. So P4 DPDK basically allows you to build a switch, a software switch. That switch sits on top of I/O ports, right? And that's what the DPDK mainly provides, the capability to receive and transmit packets very fast. So that's why in order to build these I/O ports of the switch, our first choice is basically DPDK. And over here in this little box, by the way, all the blue boxes means that this component is in place already. We have it. All the yellow colored boxes mean that these boxes are still a work in progress. They are not completed, but they are on our roadmap. Okay, so DPDK provides. It's our first choice for providing the packet I/O here, because we can do that really fast with the DPDK Polmo drivers in user space. So that's what this NIC I/O port on the left hand side is. We can also connect multiple so-called pipelines, basically that would translate to a P4 parser, deparser, and also main control blocks. We can connect those pipelines together using ring buffers. We can also use TAN-tap devices to send and receive packets with the Linux kernel. We can also read packets and write packets to pickup files. We have a drop port to drop packets. That's how we implement the drop action. We simply send packets to a predefined port of the pipeline, that is the drop ports, and all the packets get dropped. It's sent there. We have all the we have the main match tables, table types like exact match and wildcard match. These are already implemented. We have the LPM table on our to-do list, as well as the action selector. That is part of the programmable switch architecture, the PSA specification from p4.org. We have support for packet headers, for packet metadata. We have support for actions and the pipeline itself. Both of them, so basically the actions and the apply block of the control block are implemented with something that we call instructions, and we'll talk about it on the next slide. So basically, we turn the P4 application into a P4 virtual machine that crunches some predefined instructions that are part of the program, and these instructions, as opposed to eBPF, for example, which works with low-level objects like addresses, pointers. In our case, our instructions work with the high-level objects from the P4 program. like headers, header fields, metadata, tables, actions, so on and so forth. We have a mechanism for table updates, which is atomic. You could do atomic updates to tables. You could actually update multiple tables atomically. Basically, the pipeline sees either the previous copy of all these tables or the final copy of all these tables. It doesn't see any intermediate or non-consistent, inconsistent content in any of those tables. We plan to also implement aging support for tables. We have interfaces to build external objects and external functions. Some of the objects that people might typically view as external, for example, meters, we ended up implementing as instructions for better performance and integration. So things like meters, counters, registers, they are built as instructions, and objects in the P4 program in our backend, in our DPDK backend, as opposed to using external interface, obviously for better performance. We have support for internet checksums for IPv4, TCP, UDP headers. We plan to implement, connect basically our switch with fixed function blocks, right? Like traffic managers, like crypto, also replication and mirroring is on our roadmap. We can easily do recirculation using these ring IO ports that I mentioned before. We have support for this spec file, as we call it, a .spec file. It's actually the file that contains our internal representation. It's the one that gets generated by the P4 compiler and gets loaded by the target running the DPDK agent. We have a sample target agent in DPDK that is CLI based and has a few features, quite a few features. Obviously, it could be improved on the CLI side, adding more CLI commands and making it look better. It does connect through the network. It expects basically messages through the network. Currently, these messages are strings. We plan to update to introduce P4 runtime support to replace basically strings in this transfer of messages. What else? We also plan to implement a version of the DPDK softnik using P4. So basically allow people to create P4 programs that represent a NIC, describe the NIC pipelines in P4 flexibly, and then make that look, abstract that away as a NIC as opposed to an application. Might be easier to consume for some applications. And of course, what we have on our roadmap is we have more use cases that we want to implement and make sure that we do support, basically implement with P4 DPDK, write in P4, run with P4 DPDK, and see that they work correctly and they have the right performance. We have a list of changes. Some of them are fundamental on our roadmap in order to provide even more performance. I think the current performance is decent, but there are ways to get much more than what we have right now, and we plan to do it. And obviously more documentation. The current documentation is far from being great, so we are working to improve that. Please bear with us. So now Han will guide you through what's happening under the hood. Han.
So as Cristian has mentioned, the output of so as Cristian has mentioned, so let me talk a bit more about how can you use P4 DPDK to compile your P4 program. So in order to use P4 DPDK framework, it involves several steps. The very first step is an offline process where you have to take the P4C compiler and use it to compile your P4 program. And the output from that P4 compiler is something called the spec file, which is sort of the specification you use to configure the CPU data paths, right? So within that spec file, we have definitions for P4 objects, such as headers, metadata, action, and table. And each one of these objects are instantiated in data plane as a in-memory object. And then, of course, we also have the data path, which is the control flow logic, where you can apply a table in different sequences, and that's also described in the spec file. The the P4 actions and apply blocks are translated into instructions, which is we have documentations in DPDK that defines the set of instructions that we support. To give you some example, we have instructions for emitting and extracting, emitting and receiving packet. We have instructions for arithmetic operations, and we have instructions for the external operations such as meter and counters. So these instructions are at the moment interpreted by the P4 DPDK framework. However, we have plans to improve it so that they can be executed at a much higher speed as in the native x86 instruction set. So the external controller takes the spec file, and during initialization time, it will set up the data path with the all the objects described there. And at the runtime, it's going to perform a table update and also retrieving statistics from the data path. On the data plane, there is a control plane agent, right? That is responsible for facilitating the communications. In our case, this is going to be a runtime agent that supports P4 runtime. And each pipeline can be created on several CPU cores, right? Depends on what your device platform is. And these CPUs can communicate through each other, and they can work together to process the packet. Currently, each pipeline is a single thread process. We reach the higher performance by instantiating multiple pipelines on multiple CPUs. Cristian?
Yeah, thanks very much, Han. I'm sure there are lots of questions on the internals, but obviously we don't have as much time as we would have needed to explain all these. Also, we'll try to provide more examples. There is an example right now. There are some examples in the P4 GitHub repo and some examples in DPDK as well. We are working to provide more examples for people to take a look at and use as reference. So this is our final slide here. We have a call to action to the P4 workshop, all the P4 workshop attendants. The P4 DPDK project really needs you. Really needs your help. It would be great if people could help by looking at the P4 DPDK project. If you guys have applications, networking applications that you currently have implemented in other frameworks, like in C, for example, straight DPDK applications or other types of applications, it would be great to take a look and see if you can code the data path in P4. It should be much quicker to describe it, much smaller and easier to read and maintain. And please try to run that your application, your P4 application with P4 DPDK. Let us know if you find any issues, if you or bugs. Workarounds would be nice if you guys have developed some workarounds. We are not gonna oversell this to you. There are still items that are work in progress. So you might get things that might not be supported. You might need to tweak a bit the P4 code in order to get around some of the issues that we currently have, but we obviously plan to fix all of them over time. Obviously, code patches and bug fixes and new features are also highly appreciated. Thank you.
Awesome. Thanks, Cristian and Han. This was an awesome talk. And thanks for giving us the lay of the land for P4 DPDK. I guess it's the latest and greatest new P4 target. Cool. So I guess the first question, maybe it's a burning question for folks. Like, I know that there's 3 GitHub repos and you kind of walked through the architecture here, but like if I wanted to get started right now, like if I wanted to run this today. Where do I start?
I guess if I have to take this first, or I guess you have to download the to clone the two repos, right? The P4C GitHub repo and the DPDK latest repo. Then you simply need to look to either take an example from there and try to run that example, or you might want to code your application. You might have a P4 file yourself with your application. What you need to do is basically this two-step process. You need to run it through the P4 compiler, get the spec file, and then you need to run the DPDK application. That application that is called pipeline is the target agent. Run that on your CPU. Give it a bunch of CPU cores. Give it a bunch of memory. And let it basically load your P4 file and make sure that you start pushing packets through your application, and hopefully you see them on the other side correctly.
Awesome, cool. Yeah, looking forward to trying that out.
Han, anything you might want to add?
Well, I guess the question is we probably need to provide better documentation there. So we have some limited documentation on P4C and also some documentation in DPDK. We'll work on getting that streamlined so you can have a great get started experience.
Cool, thanks. So you mentioned that, if you have your own use case, you may want to provide your own pipeline. And typically when you're writing a P4 program, that typically involves picking an architecture. So is there a P4 architecture that you recommend or that is supported? Are there multiple architectures that people can use?
Yes, at the moment we are targeting the P4, the portable switch architecture, the PSA architecture. So that's the default target that you should write your P4 on top of. The reason is the PSA architecture defines a switch architecture that can be ported across different type of devices. So you can write a P4 program that's targeting, say, a switch. You can also run it, the same, more or less the same program, run it on P4 DPDK, without changing your control plane software. So we think PSA and the combination of PSA and P4 Runtime is a good target for us to support. So that's what we do as of today. There is another architecture called portable NIC architecture, which is on our roadmap to support.
Yeah,
awesome.
Maybe one more thing to add here. Obviously, the PSA architecture, a portable switch architecture, is more targeted to a big iron switch. There are a lot of things that are great and portable and reusable on the CPU. But on the CPU, maybe over time we want to create a better architecture that is more suitable for multi-core CPUs. One example here, so on a CPU you have many cores. On each of these cores you can instantiate one pipeline or even more pipelines. So a fixed topology like an ingress pipeline followed by a traffic manager and followed by an egress pipeline might not work for everybody, right? You might also have encryption blocks or any other fixed function blocks in your application that you want to connect with lots of other pipelines in whatever topology that you might have. So while it's great to have PSA as a reference architecture with all the externs that are there in PSA, that would work great, I think, for a multi-core CPU architecture. It would be great to loosen up a bit these restrictions and allow in a multi-core architecture allow more flexible topologies of pipeline.
Cool. Yeah. Thanks for the insight. And when you mention things like encryption blocks or maybe tunneling, compression, these sorts of things, I mean, are these modeled and available to the P4 programmer? Are they externs in your world, or how does someone use one of those blocks? That's
a great question, Brian. We thought about this, and there are different approaches that people could take. So, for example, we could march on this concept of intrinsic metadata. and just try to add, for example, packet color, traffic manager queue, and all sorts of parameters, attributes to let's say a common interface, a common packet interface. I think that might not work for the range of fixed function blocks that we have to deal with in on the CPU side. Is more than just traffic shaping, management, replication, mirroring. As you mentioned, cryptography, compression, and all those things that we had on one of the previous slides. So one way to do that we are thinking of doing and prototyping is not yet done, but we'll probably start with the traffic manager because there is a traffic manager in DPDK. There is a library, a software library to do that. We simply want to have the pipeline create a custom header and put it in front of the packet. So let's say you need to send out the Ethernet frame. If you know that you need to send that Ethernet frame out to a crypto accelerator, for example, you just put a custom header in front of that Ethernet header of your frame and put there the encryption key, put there the nonce, the IV, the whatever other parameters your encryption algorithm needs, put them as a key in front of that, specify your algorithm that you need to encrypt or decrypt the packet, specify your hash, whatever else you need, put it as a header and send that packet to your traffic, to your fixed function block. That might run on a different CPU core, and that accelerator really, it could be a hardware or a software accelerator, could be software running on that core, or maybe that core is simply working with an external hardware accelerator. Basically, on that core, decap, take out that header, which is essentially just metadata for the operation of that block. Interpret it, get to your keys, get whatever you need, invoke your operation, and then eventually, once you have encrypted or decrypted the packet, you finish your fixed function operation, send the packet back to the pipeline. You can inject it on another input port that could trigger some different actions, right? So you essentially inject that packet back into the pipeline, not necessarily from the very first logical stage of the pipeline, could be somewhere in the middle of the pipeline if you need to do that.
Well, yeah, that makes a lot of sense. And I guess the picture that's maybe starting to emerge is one where we shouldn't think of P4 DPDK as a single switch, but we should be thinking about the switch as a network fabric. And we can run various pieces of pipelines on different cores and then use other cores for accelerating blocks like you're talking about. So instead of like writing one P4 program, you have a P4 program that dumps a packet off on a DPDK port and then comes back in, and you can really have like a whole topology of functions that can be invoked on a single board or host.
Yeah, that's a great point, Brian. And also, I guess the key point here is performance, right? It's a very compelling, a very tempting picture that you are building. But the key point is getting the right performance, right? We can do all these topologies, but we also have to make sure that the performance is good enough. Otherwise, they won't be that useful.
Yeah, and then that's maybe a great segue to another area that I think a lot of people are interested in. When we talk performance, I guess we can talk in terms of things like network performance, packets per second or latency numbers. We can also talk in terms of cost, right? What's power and number of cores and other things. Are there initial set of benchmarks or rough numbers you can provide in sort of the performance space for the solution?
We are not ready to share public numbers. We need internally to get through some procedure to release performance numbers externally. But yes, we are building. We have a set of unit tests, and we are building more examples to share with people. So then people could simply take those examples and run for themselves, right? And see for themselves what the performance is. It's cool. It's basically measured in millions of packets per second per CPU core. But obviously, performance, your mileage may vary a lot depending on your application, obviously. How many tables you have in your application? How many actions do you have in your application? How many things you are doing per packet, right? How much parsing you are doing per packet? Are you simply peeling 10 layers of an onion, 10 layers in the onion, right, in the packet? Parsing is one of those operations that is expensive. And by the way, that on the CPU, and by the way, that's one thing where we need to talk to people, to the community, and find a good way to couple the parsing that can be done on hardware NICs that essentially are the ports of this switch, with the parsing that cannot be done there, and you really need to do it on the CPU. So there are obviously the current NICs, the current network interface cards are very smart at this point, and you can do a lot of filtering. You could basically do that parsing on the NIC side and put different packet types in different queues. So then your pipeline on the CPU, running on the CPU, doesn't need to go through that again. It simply knows that, hey, in Q0 you have TCP packets, in Q1 you have UDP packets, and in Q2 you have GTPU packets, for example. So then it could simply extract those headers without asking or without looking into the packet to see what headers are there, discover those headers.
Got it. Thanks for the explanation. Maybe changing gears a little bit in sort of the experience side. So DPDK has an interface and a set of instructions and things. P4 has its own view of networking constructs. Were there any constructs that were particularly hard to map between the two abstractions, or anything that didn't quite fit that you are still working on?
Well, there are a lot of opportunities for improvement, right? To be blunt, PSA specification was developed with hardware switches in mind. But it is still a good enough reference for us to implement on the CPU side. Now, for example, I'll give you just one example on the header emit side of things. It's quite a nasty operation to do it on the CPU. Essentially, you have to wait until you get all the emits that you need to do for the current packet. And by the way, some emits could be the emits for current packet could be different from the emits from a previous packet, for example, because you could have some conditional logic in your program, right, to emit some headers or other headers. Essentially, you have to wait until you get your last emit, and you have to translate that into a scatter-gather list. And you have to copy small bits of data, which are these headers, from one place in memory to another. And that's not something that you can easily implement on the CPU. It might work much better on a switch where you have dedicated hardware to do that. Not as great on the CPU to do that. There are others as well, but sure. I'm not going to go into detail.
Yeah, there are other things regarding the CPU target. You know, in P4, the width of the field are pretty arbitrary. You can say I have a 1-bit field. I work on that 1-bit field. I concatenate it with another 1-bit field. But on the CPU target, things works more at the byte granularity. So the compiler has to do extra work to either pad it up to byte boundaries, or the programmer has to pay extra attention to these kind of issues so that it can be executed efficiently on the CPU target. So there's some minor issues with respect to the P4 and the CPU.
Yeah, awesome. And I think that, you know, these are definitely interesting design points that probably can be brought up within some of the P4 working group sessions as CPUs become a bigger target going forward. So maybe my last question has to do with some of the in-progress developments and timelines. Is there a timeline for some of the yellow blocks you had in the previous slide, or any interesting milestones you have coming up in the near future that you want to share?
Sure. I mean, obviously, we want to implement them all, but it's not always easy to parallelize work for all these items. Some of them simply require some rework as you go from one to the other. You might have to do a bit of rework. So I think on our immediate roadmap, the cool features that we want to add next are the action selector and the LPM table. Going forward, we also want to add fixed function blocks like traffic management and the cryptography that are already supported in DPDK, for example. We want to fix the packet mirroring and cloning. We definitely want to add more documentation. Maybe we should stop all the development and we should just focus on documentation for a while. I'm sure the users will be delighted, but probably not everyone. I mean, there are lots of people eagerly waiting for more features. But I guess documentation is key as well. As well as performance improvements, as Han mentioned, we have some experiments in progress on how to get more performance by avoiding basically the interpretation of instructions at runtime. As Han explained, we do translate those instructions from strings to some low-level constructs like binary numbers, pointers, everything you need at runtime just to go do it. But still is not good enough because basically each instruction translates under the hood to a function pointer. So basically, if you execute 50 instructions per packet, that means you call 50 function pointers per packet. And the bad thing about this is the fact that the GCC compiler can only optimize each function individually. But if we could basically translate into, let's say, a more compiled version of the program, where GCC would see the entire code, then GCC would be able to do a much better job at optimizing the whole action, the entire action as a whole, or the entire apply block as a whole. So that's another very important thing that we have on our roadmap.
In terms of release mode, from the compiler perspective, we're basically, as we implement new features, we're going to put them onto the master branch of P4C, so that feature becomes available immediately to the community. On the DPDK side, I believe there's 3 months or 6 months release cycles. So the patches are added to DPDK and they will be available for the next release. Or if you're really keen on trying that feature, you can try the development branch.
Yes, so basically on DPDK side, our plan is to the DPDK community plan is to get a release every quarter. And by the way, I think we are just working to finalize the 2105 release, basically the May 2021 release. But I mean, it's always good to get a release. The November release is a long-term support release as well. So every year we have a November release that gets supported for several years. All the bugs that are found are retrofitted back to that version. But also, as we develop new features, we just send patches. They will get integrated on the main branch with some delay, but the patch is there in DPDK patchwork. People can pick it up and apply it. Although it's obviously not ideal, there are ways basically to avoid having a long delay if people need that.
Well, yeah, thanks for that insight as well. Is there anything else you want to add, either of you, before we close the session? Anything that you've thought of that we missed that you want to say?
I think we said too much. We greatly exceeded the time.
This is all great information. Cristian, Han, thank you so much for spending your time with us today. Looking forward to trying this out, and hopefully I can reiterate your call for participation. Download the repos, try it out, send fixes and send comments. This is all pretty awesome.
Thanks, Brian. We really look forward to your contributions and everybody's contribution as well. Thank you.
Thank you, guys.
Everyone.